Hey, AB Calculus. Today we are still in chapter 18. Today we're going to be looking at Rolle's theorem. All right, Rolle's theorem. So named after Michel Rolle. I don't know how to say it for real. Rolle's theorem is, it's another one of these existence theorems where we have to show that I have a bunch of stuff, and if I have that stuff, then I know something. And it's not super specific, we just know that something happens between 2 points. So let's see if we can read the theorem and pick up the information. So this is where I'm going to shorten what Stu talks about. So let f be continuous on the closed interval from a to b and differentiable on the open interval from a to b. What we generally say is, and I'm going to use C to mean continuous today in this video and D to mean differentiable. So if f is continuous and differentiable on a less than x less than b or a to b, if this, so that's one of the things that we need. We need it to be continuous, we need it to be differentiable, 1, 2. We also need f of a to equal f of b, okay. So it looks like we need these three things. So if we have these three things, we can say, then by Rolle's theorem, there exists C on A to B such that f prime of C is equal to 0. Let's talk about this in a common sense way, see if it makes sense, and then yeah, do an example or two. So I put the 3 dots here. Rolle's theorem, you have to show these 3 things are true. If these 3 things are true, boom, Rolle's theorem happens, done. All right, so let's look at a situation. Here's A, here's B. I know that these 2 dots are equal to each other. And I know that my function is continuous and differentiable. Let's look at possible ways to connect the dots. Oh, by the way, continuous and differentiable. This is continuous, but this is not differentiable. Remember, it's not differentiable at that point, you know, or the cusp thing, like not differentiable at that point, so it's a problem. And continuous, like there's not gonna be any breaks like that, not gonna be any asymptotes. It's gonna be a smooth curve from A to B. Draw a smooth curve from A to B. Well, one option would be to draw a flat line. What would f prime of this flat line be? Well, if a flat line is like y is equal to 5, well, f prime of that, y prime of that is equal to 0, right? So in this situation, sure, there's some f prime, we could say there's at least one C, because this one is 0 a whole bunch of times. We have a derivative of 0 a whole bunch of times. Remember, a derivative of 0 occurs at minimums and maximums, local mins and local maxes in curves, at bumps, peaks and valleys. So what's another situation? Well, we could be like, well, it goes up, well, I gotta come back down at some point, right? Or like, goes up really high, gotta come down at some point, okay. Or like, goes up really, really high and then comes down, like swoops in. Or like, whee! Regardless, each of these has at least one peak, and that would mean the f prime at that peak is 0. Well, what about if we went down first? Whoa! Well, I gotta come back up somehow, and I gotta be smooth. Oh, but then I go back down, whoa! Doesn't matter. Hey, look at that, look at that, look at that. Oh, I missed one up here. Each of these places, we would say f prime is equal to 0. So hopefully you can see that regardless of what happens between the two, as long as it's continuous and differentiable, that smooth curve, as long as it's like that, it's guaranteed that f prime, that the derivative of f is going to be 0. The slope is going to be 0 at some point between a and b, at least one time. Could be a whole heck of a lot more. So that's Rolle's theorem. Let's do an example. Show that Rolle's theorem holds between two x-intercepts, shown on the right. All right. X-intercepts. Oh, right, because y is 0 at an x-intercept. X is equal to x squared minus x minus 12. So what is that going to be? 3 and negative 4? No, negative 3 and 4. Okay. So we're looking at the interval from negative 3 to 4. We can say we know that f of negative 3 is equal to f of 4, which is equal to 0, right? That's true. So that's one of the three things that I need. Is it continuous and is it differentiable? Yes. Why? Okay, so since, by the way, I'm fine if you use like bullet points when you go through this. You don't have to do a paragraph thing. So because we have all this information, we can say by Rolle's theorem, and we don't have an abbreviation for that. I use THM for theorem, but we don't have an abbreviation for Rolle's theorem. By Rolle's theorem, there exists at least one C on negative 3 to 4 such that f of c, nope, f prime of c is equal to 0. I'm guaranteed to have like a place where the slope is 0. And if you look at the picture, yeah, we're guaranteed to have this slope of 0. So Rolle's theorem does wind up being a useful theorem for us. Minimums and maximums wind up being really, really important, and minimums and maximums occur oftentimes when the slope is 0. There's other times they can occur too, like when the slope is undefined, like we saw in that, we can have a minimum or a maximum at these kinds of things, but when we're dealing with smooth curves, minimums and maximums generally occur when the slope is 0. So it helps us find critical points. You might remember talking about critical numbers when we were talking about physics. All right. Now, find all values between the non-zero x-intercepts for which Rolle's theorem holds, shown at the right. So in this situation, it, instead of just saying, hey, does Rolle's work? It's saying, show me all the places where it actually happens. So that's between, we have to find the x-intercept. Okay. Because it's like, McDonald's. Okay, so we got from here to here. We're trying to find all the places where the slope is 0. So, I don't know those, I need to find those intercepts if I want to like be technical, but it's just saying find. It's not asking me to like back anything up, or like in this one where it says show that Rolle's theorem holds. This is where we would need to be more technical. Since it's asking me to show Rolle's theorem, I need to use all like the, I avoided using the word in the last video. I'm proving that this is true using Rolle's theorem. So with a proof, we need technical information. This is just saying find, so I don't really care what those are. I could solve for them and find them. Pull an x squared out, get 3 minus x squared. So solving that, we get 0. Solving this, we get x is equal to plus or minus root 3. If you ever need more detailed stuff than this, please let me know. I'd love to spend some time with you helping you learn how to solve these easily. All right, so in this situation, it's saying, hey, so when does f prime equal 0? So we can do something similar here. We can set it equal to 0. I can factor a 2 and an x out. 3 minus 2x squared. So this one, x is equal to 0. So that's one place that it was guaranteed that at least one of them happened. So there's at least one. But if I look at these, let's see. So 3 is equal to 2x squared. So x squared is equal to 3/2. So x is equal to plus or minus the square root of 3/2. So I have 3 different places where I have a slope of 0. And all 3 of those places are between the square root of 3 and the negative square root of 3. All right. So then for this last one here, find the values of C guaranteed by Rolle's theorem. Rolle's theorem guarantees f prime is equal to 0. So I'm really just saying, hey, f prime equals 0, and then find it. So that should be the end of Rolle's theorem. Yep. So that handles up to number 12, I believe. Yep, that handles up to number 12. So shorter video this time. Now that the groundwork's been laid, we can go through these theorems a little bit faster. So hope that was helpful. Bye.